In this video, we are going to work on review the statistical inference when we have more than one sample or more than one population. So far, we learned about case 1 and case 2 when we have more than one sample or population. So we are dealing with different sets of data. What would we do? So here we are going to learn that, okay, so what if we wanted to know that what's happening between their variance? So it's like this. We said that case 1, and I'm talking about the situation that we have more than one set of data. So case 1, we are into the parameter of interest is the difference between the two means, for example, and we know the variance, which rarely happens. Case 2 was where we talked about the times that we are interested on mean, like the difference between the means, and we don't know the variance of the population. So it's like that we don't know what's the sigma 1 and sigma 2. So in that case, we would say that, okay, so what about if the variances are close or equal, or what about the variances they're not equal together? So that was the two situations that we had in case 2. So now we want to know that, okay, how can we make sure that if these variants for case 2, they are equal or they are not equal? In this situation, we have another case, and we call it case 3. In case 3, the parameter of interest are the parameters of interest are like sigma 1 and sigma 2. When we were working with the case 3 in the second year stat, and we had just one sample, so we were working on just one variance, and we wanted to know that what's happening with the variance. So we would go and use the chi-square table. But when we are working with more than one variance in case 3, so the parameter of interest are variance, but we are comparing two variances together with each other, and we would use F table. I'm going to show you both of the tables like today or later in the course, or in the summary sessions, one of the summary sessions that we have. But basically it's like this. The reason that we have case 3 is that because when we are working with case 2 and we don't know the variances like are equal or not, we need to have more info. We don't know anything about the variance, right? So we want to know that which situation we are in, so we need to have more information about the variances. So we would go to the case 3 and find out that if they have if the variances they're equal or not, and then we would go back to case 2. So let me share my screen with you to have the notes. Okay, look at here. It's essentially in case 2a, we can make the assumption that population variances 1 and 2 are unknown to us, but sufficiently close, like they are equal. We can consider they are equal and proceed with the use of the pooled variance. But is that a good assumption? So here is that then we need to go to case 3, and we would need to analyze the standard deviations like individually, go to the F table, compare the result. Like you would have a new F test or the test statistic. Like t-test, it was test statistic, right? Z-test, it was our test statistic. So here, F-test is going to be our new test statistic. Look at this example. Two companies, A and B, produce polycarbonate pellets. Here are the summary statistics for two samples that we have. So we have the N are the same, 100 and 100. X bars are very close, but the variances is different. So the standard deviations are different as well. So the pellets seem to have the same average weight, but there is a difference in the weight, in their weight variability. So their variances are different. We want to make some judgment about the sigma 1 and sigma 2 because we don't know the variance. So when you look at it, if the parameter of interest was mean over there, the means were very similar, right? If they were, we were interested to find out the difference between the mean. We needed to know, because we didn't know the variance, so we needed to know that if these variances are close enough that we would use the pooled estimate method, like the equations, or we would use another new like degree of freedom when they are the variance, they're not close together. But we don't have any clue right now. So what are we going to do? We are going to move to case 3. Like we would compare S1 and S2. Look at here, we can examine the difference between using an F test, which involves the ratio of the two variances. So S1 over power 2 over S2 power 2. And when testing for differences, we try to have the smaller observed variance in the denominator most of the time. You will see cases that they don't do that, but let's do that all the time. Let's consider it in the smaller in the denominator, that we would, when we want to make judgment later, we always remember this, the smaller one is in the denominator. So the test H null is going to be sigma 1 power 2 over sigma 2 power 2 is equal to 1. So here, in fact, it's like that. H null says that variances, they're equal. H1 says that variance, like for the sample 1, is greater than the variance of the sample 2, right? And we said that the smaller one is going to be in denominator. So sigma 2 is the smaller one here. Then the null hypothesis above says that the two variances are equal, as I said. Okay. So now, F distribution, because we are F distribution and chi-square distribution, when you're looking at the distribution, you will see that they're tailed. They are not symmetric. If they were symmetric, they would represent some normal distribution, and probably we would consider, because it's like that, we would have a variable that we can consider in our regression model. So when we are talking about the F distribution and the chi-square distribution for the variances, if you have one sample, it would be chi-square distribution, and if two samples, it would be F distributions. They look like similar a lot. The only thing is that in the F distribution, we are going to have two different N, because we are dealing with more than one sample, right? We are comparing two samples. If it was chi-square distribution, we would work with just one sample, so it would be 1 degree of freedom in it. If you look at the tables, you will see. But the shape of them is very similar. They're not the normal distribution. It's representing variability, right? So they can't be normal. We can't say that they have a normal distribution. The F distribution requires two numbers to define its shape. So we would say F of the degree of freedom of the numerator and degree of freedom of the denominator. So for the numerator, we would say n1 minus 1, and for the denominator, the degree of freedom is going to be n2 minus 2, very similar to the degree of freedom that we had for the t-table. And when we are looking at the F-table, I'm going to show you quickly the real F-table as well, but we will see that on top. So you would have the degree of freedom of the numerator, and then you would have the degree of freedom of the denominator. And we have different tables, F-tables. Like, for example, we have one F-table. On top of the table is written that this F-table is for the alpha equal to 5%, or this F-table is for the alpha equal to 1%. So you can see these numbers, it's very different. If it's like you are working with the 1%, alpha equal to 1%, like 99 confidence interval, in that case, your value for F, they're very big. Like they're larger than the, when you are working with the smaller confidence interval. It makes sense. Think about the error, right? So the F-table, like the variation that you would have when you have a larger confidence interval, it means that, so the confidence level larger, so the variation is more as well, right? So the F-table, the F value would be large. The F-table above is for 5% and 1% significance level. It provides critical F value that are cutoff values for those probability. So before going to the next slide, I'm gonna show you the F-table. Stats table, this is F-table. Yeah, so look at here. This is typical F-table that we have. So here, this one, the F-table is for 0.05. And here you have the degree of freedom of the numerator, degree of freedom of the denominator. So it's like that if I have two samples, I would see that which one has a smaller variance, and I would consider that one as my denominator. So my And then I will read the n that I have for each of these, like for sample 1 and sample 2. And whatever degree of freedom that I have for the numerator, I would find it here. And whatever degree of freedom, like n2 minus 1, right? I would find it here. And then I would read the f value for it. So this is the f of the critical. This is the f from the table. So I need to find out the f as observed value and compare my f of the observed value with this f of the critical and make a judgment, right? So because this is a hypothesis testing that we are talking about, the comparing like the variances together. So let me show you go back to the slides that we had. Okay, sure. So when we want to read the F table, first we need to choose our level of significance. Why? Because if we have the table that we have for for example, level of significance alpha of the 1% is different than the level of significance for the alpha like equal to 5%. So we would use we would choose the different F tables, and then determine your degree of freedom of the numerator and the denominator from the respective sample size. Look up for the critical F value, like the same things that I did like a few moments ago. If calculated ratio is greater than the calculated of the critical F value, then you would reject the null hypothesis. The variances in the ratio seem significantly different. So it's like that. When we reject the null hypothesis, we said that null hypothesis is like that S1 or sigma 1. We said that sigma 1 power 2 over sigma 2 power 2 is equal to 1. That was null hypothesis. So we would consider the variances. You can say sigma 1 over sigma 2 is equal to 1 as well. One is the square root of the other one, right? But it's like that when I reject the null hypothesis, it means that sigma 1 and sigma 2, they are not equal. So that's the reason that we would say that when we reject the null hypothesis, therefore the variances in the ratio, like sigma 1, sigma 2 that we would have, sigma 1 power 2 and sigma 2 power 2 that we would have, they would seem significantly different. They're not equal. So here is the example that we had. Let's do that for it to see that how does it work, how would it work. So I have the plate weight example. So I have the variance of each of them. It was written in the table like 2 pages ago, like 2 previous takes. So I would have the 100 minus 1, like the degree of freedom for each of them. And then I would say that for F observed, I would divide the variances. So the variance of the SB power 2, so this one is 1.64 times 10 minus 5. So this one is greater than this. So the smaller one would go to the denominator. I found 7.29. And then from the table, we find that when we go to the F table and find out for the alpha level of significance of the 5%, I would find that the F critical, like go and look at it by yourself. So you do 99 and 99, then you would get the value is 1.4. So you can see that the F observed here is a lot larger than the F of the critical. And we said that when the F observed is greater than the F from the table, we can say that the variants are significantly different from each other because we rejected the null hypothesis. So remember this all the time, that we would reject the null hypothesis if F observed is greater than the F that you will find out from the whatever it was from the table. It's very similar. Think about the logic that we had for the T table. So we said that if the T observed is greater than the T critical, it means that we are outside the null hypothesis region. So here is the same. So we reject the null hypothesis. Look at this. We have an example with the name like in the tutorial section of the course note on Learn, and it's like the file's name is chapter 1, the document chapter 1 example 6. So it's you will see an example on obtaining the confidence interval and a variance. Because when we are working on the hypothesis test, it doesn't matter. Like if you know how to do get the hypothesis test, you would be able to do the confidence interval. If you know how to do the confidence interval, you would be able to do the hypothesis test. As I said, they're very similar, just the starting point is different. So the next thing is correlation. I'm going to talk about the correlation in the next, like in another video. For now, let's just focus on the hypothesis test and confidence interval for when we have more than one sample for case 3.